to you if you got it. Okay. Great. All right, welcome everyone on Zoom. Can you hear us okay?
Yes.
Great, thank you. It's my pleasure to introduce Tianchen Qian, who he was a student here and worked with me, with Constantine. Are there others who I think it was so it's so we're really honored to have Tianchen coming back, and it's just very happy to think of the great memories. But Tianchen has gone on to do very impressive work. He was after graduating here, did a postdoc with Susan Murphy, and after that became faculty at UCI, UC Irvine, in the stat department. And I just want to give a very warm welcome to Tianchen for I really appreciate this, and we're excited for your talk.
Yeah, thank you. It's so great to be back here at the JSPH, I used to call it. And I would like to share with you some of my recent work on something that combines causal mediation analysis.
Can the Zoom folks still hear okay?
Yes. Okay.
So maybe
it is good to be like behind. It's best if you can be behind the microphone, but
I see. Okay, I'll do that.
Oh yeah, it's way better. Thank you.
Okay. So the combination of causal mediation analysis and then a particular type of experimental design called micro-randomized trials. So I'll walk you through what they are and then how they interact with each other and some interesting statistical questions that come up. Okay, so I'll first give an overview of the study design and then talk about two particular challenges that arise in this particular study. And then we'll talk about estimation and then see an application. So the application area I collaborate the most on is called mobile health interventions. So you can think of them in the form of mobile apps like fitness trackers, mindfulness reminders, medication reminder, drinking dairy. They're designed to change people's behavior and promote healthy behavior change. And the mission of the field, we work with lots of domain scientists, behavioral scientists, psychiatrists, is to deliver the real-time personalized behavioral support, essentially sending say a prompt or a message at the right time to the right person. So there is always an assumed mechanism in mobile health interventions research. So we'll see some example of the intervention prompts, but in short, it's always assumed that the prompt would promote some short-term behavior change, like taking a walk, or maybe record something for your day, and then it would in turn lead to some long-term behavior health benefits, some improvement on the clinical outcome. So you see that here is a assumed pathway or chain of actions for the intervention to take effect. Here are some more specific examples. On the top, we have a physical activity app. It can send activity prompts like push notifications or messages, which would increase or hypothesize to increase the short-term physical activity level, which would in turn influence long-term cardiovascular health. At the bottom, we have the smoking cessation example, where the researchers have designed various types of coping prompts or prompts recommendations for self-regulatory strategies. And these maybe lead to short-term, the person practicing mindfulness exercises to cope with their urge, and that would lead to long-term abstinence or increase the chance of long-term abstinence. So these are examples of these assumed mechanisms. This is a key premise in all these research, but it's often just assumed and not validated. So the question we want to ask is, can we verify this premise empirically? And to make things more concrete, I'll describe a specific study called the HeartSteps Micro-Randomized trial. So this is a study that the researchers wanted to design and optimize these phone push notifications to promote walking. So there are 37 participants in the study. Each were repeatedly randomized to either receive a prompt or not receive a prompt for 210 time points. So that is calculated as 5 time points per day for 6 weeks. The long-term goal is to improve activity level and improve cardiovascular health. Here's some example of the prompts. So to your left, you see a prompt saying, how about taking a few minutes to enjoy nature, head outside and walk until you see a wild animal. And depending on where you're at, maybe seeing a squirrel can take a long walk. And to the right, it's a stretching suggestion, recommending you to stand up and stretch for a little bit. So I'm going to dig deeper to be more formal about the structure of the trial. For each time point, each participant in each of the 210 time points, we observe XT, their time varying information, their location, weather, activity level, etc. And then a randomization occurs. In this particular study, the randomization is pretty simple. It's 0.6 probability to send a notification to the person and 0.4 to not doing anything. Okay, and these probabilities were designed so that on average, a person would receive around 3 messages per day. So that's deemed a tolerable amount for these individuals. We have other studies where the randomization probability can change depending on the person's history information. And then we observe some outcome, some short-term outcome. Here, I call that MT because we'll look at them as mediators. But these are step counts. The participants, they wear a sensor all the time, a jawbone sensor to track their step count minute by minute. I see this was, that was from a while ago. Okay, so here's the notation that we'll use moving forward. We have these pairs, these X, A, and M pairs, the triples, covariates, treatments, and mediators varying over time. And then at the end of the study, we measure some kind of health outcome. I denote that as Y. So I want to emphasize that here, I am not making any assumption about the causal structure between all these variables. So the big arrows just means that you have every node pointing in the left, pointing to every node on the right. So not making any, for example, Markovian assumption. And in fact, for these mobile health studies, we do want delayed effects. We want the push notification to gradually build habits so that the people, they can sustain that healthy behavior in the long term. Okay, so that's our notation. And there are some causal questions that's already been answered in the literature, and I want to give you a brief overview of that. So when this type of design came out in 2015, the most straightforward question is, does the prompt change your immediate behavior? Does sending a message increase your step count in the next, say, 30 minutes, 60 minutes? So that's the short-term effect. Does AT influence MT? And there's some literature already tackling this problem. Now, the next question is, does these push notifications change the clinical outcome, the long-term behavior? Does AT influence Y? Now here, even though I'm saying just A for a specific T, actually we will be, the literature tries to model over the course of the study so that this is not just a single AT. There was some recent work by my group on this topic. And then you see that in the hierarchy of questions, the next question naturally is, does AT influence Y, the long-term outcome, via changing the short-term behavior, MT? And that's what this talk is about. And by the way, feel free to stop me for any questions during the talk or afterwards. Okay, so I want to present to you 2 challenges when we try to tackle this mediation problem. The first challenge is that we have many treatment occasions. We have many T's. In the HeartSteps study, we have 210 different T's. This is common for micro-randomized trials because the app interacts with people daily, and the study usually lasts for maybe a few months. We have many, many time points, many decision points. So even though in the causal literature, there's abundant work on time-varying treatments, they not necessarily generalize to this setting where we have so many time points. So it's a natural question to even, it's not an easy question to tackle, even to define the cause and effect in this case. The second challenge is that even if there is only just one treatment, there are many mediators because people's behavior is continuously recorded. And we wanted to understand, for example, for specific A, how does the effect of A propagate to Y through all these future measurements? And that's another challenge. We have many pathways to disentangle. Do we want to disentangle all of them, or how do we try to chop the problem so that it becomes manageable subproblems? We'll see how we tackle these two challenges. And before I delve into that, I wanted to give a brief comparison of the novel trial design micro-randomized trial with the classical RCT to make sure people understand these are different types of trials. So in a classic RCT, we have many experts in the room and on Zoom. And we randomize once per person at baseline. The treatment is a single one, taking values, say 0 and 1, or we could make it more general. Sometimes we look at mediators. So in order to make the parallel comparison, I include a mediator in here as well, and then we have the outcome towards the end of the study. In a micro-randomized trial, the randomization occurs, there are multiple units, multiple individuals too, but for each person, we have many, many time points of randomizations. We have a sequence of treatments, each time sequentially randomized. We have a sequence of mediators. Okay, so now look at this. Maybe you're thinking this is repeated RCT over time. You repeated the randomizing, but the purpose of MRT is not just to collect more time points so that we have higher power to detect the effect. As I said at the beginning of the study, right, the goal of these mobile health interventions is to change long-term behavior. So naturally, the focus would be on delayed effects, how to best sequence the treatments so that we achieve the optimal engagement or the optimal change in the behavior. So the temporal ordering and the interaction across different time points is a important focus on micro-randomized trials. And another thing I wanted to say is that the RCTs are confirmatory trials. We have well-developed treatment packages. We wanted to compare that with a standard of care and establish that the new treatment package is better. Whereas for micro-randomized trial, it's not a confirmatory trial. It is a so-called optimization trial. It is used to optimize the treatments. Maybe in this case could be optimize the sequencing of treatment delivery, optimizing, people use the jargon of policy, which is the decision rule of sequentially sending treatments to optimize the policy, or maybe to optimize the treatment content. Maybe we'll find out certain messages work better than other messages. So, in the grand scheme of intervention development, you can think of MRT as a step before the RCT. Once you optimize the treatment, once you have a pretty good decision rule, then you can move on to the RCT to compare, say, prescribing an app to a person versus not prescribing the app to that person. Okay. So with that out of the way, let's talk about solving the two challenges. The first challenge is that we have many, many time points. How do we even define a causal effect? And I would like to take a step back. Let's don't talk about mediation yet. Let's just think about a simpler problem where we have these covariates and treatments varying over time, and then we have an outcome at the end. With large T, how do we define the causal effect? Okay, in the context of HeartSteps, it will be, does an activity suggestion prompt improve long-term health? Still, we have too many time points. So what do? Let's give a quick review of potential outcomes notation. People in the room, pretty much, I think you're familiar with it, but I'll point out some nuanced challenges here. For single time point case, we use the parentheses for potential outcome, right? We are all familiar with the average treatment effect. In the longitudinal case, the potential outcome notation is also well established. It's been 40 plus years since the first paper by Jamie Robbins on this type of notation. So we have a sequence of treatments indexing a potential outcome. And I'll use overbar to denote the sequence of variables. So here are some examples, right? You can have 2 to the capital T combinations of the potential outcomes if A were binary. The conventional approach, the classical and very commonly used models like marginal structural models, structural nested mean models, and variations of these, they often focus on modeling either the expected outcome of a expected potential outcome and how that varies with the hypothetical treatment sequence, or they model difference. So here you see that we can directly model some kind of treatment effect with 2 fixed treatment sequences. The challenge with too many T's, now here we can be more technical, is that if we were to do something like this, there are too many parameters. When you face a problem where you have limited sample size and you have too many parameters, there are usually 2 ways to tackle it. One is that you make stronger assumptions. You make structural assumptions. For example, in some seminal marginal structural model papers by Miguel Hernan and Jamie Robbins and colleagues, they assume that this expectation depends on, say, the summation of all the ATs, or when people started taking the medication, etc. So these are structural assumptions that you can make to simplify the problem. Another approach is what we'll take, called marginal contrasts. You can think of them as maybe changing the goalpost, moving the goalpost to a place that's still interpretable, but also more estimable. So this is, I'll expand on that idea, the marginal contrast, and that's what gives rise to the more recent causal literature on the excursion effect. Okay, so suppose we have a bunch of individuals, each were in the study for 5 time points, and I wanted to understand the causal effect of the A's on the Y. So here are some, randomly assigned treatment sequences. If I were to take an average of everyone's outcome, then these orange and blue and the green colors becomes, I'll denote as rainbow colors to represent that it's a mixture of the ones and zeros. And the outcome would be expected value of Y under all these capital A's, right? So when I write things in this way, Y is random, but all these A's are also random. So the expectation integrates over the distribution of the A's. Now, we know under SUTBA, this is just expected Y. Okay, so everything should align with what you would expect in this very simple case. Now, I intentionally sorted these individuals so that to the right, everyone has A3 equal to 1. To the right, everyone has A3 equal to 0. So if I were to take an average of everyone to the left, I get rainbow color for 1, 2, 4, and 5 time points, because that's still a mixture of zeros and ones. But for A3, I have 1. So if you, forgive me for omitting some technical details about, observational studies and sequential ignorability, you can understand this average as this notation, expected Y of random A1, random A2, A4, A5, but A3 is set to 1. Okay, so this is expected value of Y under a specific treatment rule. where we have A1, A2, A4, A5 following whatever the design prescribes, random A's, and then at A3, we assign 1 always. So this is a treatment policy, or you can think, if for those of you familiar with dynamic treatment regime, this is a dynamic treatment regime. Okay, so we call this an outcome under an excursion policy because we are following the MRT until at time 3, we sort of move around to do something else. In this case, I'm assigning 1. Then I come back to the MRT policy. Okay, to the right, we can also take an average, and that gives us expected value of random A1, A2, A4, A5, but A3 is set to 0. Okay, so the causal excursion effect, or the marginal contrast that we'll use to solve the problem of too many time points is to consider the contrast between the left and the right, where A3 is 1 versus 0, but everything else are random following the treatment of the trial policy.
And sorry to interrupt it. And this all works because all of the A's are randomized independent of exogenously.
Great question. Yes, this illustration works because all the A's are exogenous. So like the A4 and A5, A4 and A5, they have the same distribution. In the more general setting where A's are sequentially randomized that can depend on the history information, the excursion outcomes and the contrast we consider are still these two guys, but the illustration no longer work because I can't just look at individuals receiving A3 equal to 1 and call it a day, right? And then one more nuance is that in that case, A4, A5, the distribution to the left and the A4, A5 distribution to the right would differ because we're considering different A3 values. But nonetheless, we will consider them and try to give an interpretation to that. But great question. Okay, so here is the total effect. Later on, we'll move on to mediated effects. But for the total effect, this is the contrast between the two excursion outcomes that we're talking about. Y under this policy, follow micro-randomized trial until t-1, then set AT equal to 1, then come back to follow the trial policy again. Right? The green is the other counterpart. Okay, so the interpretation is this. We will have to consider someone that's in the trial, that's receiving random treatments, receiving random push notifications from time to time. And then we ask, for that person, at time t, if we override the app, if we say always send at time t, versus always not send at time t, and then have that person still stay in the study till the end of study so that they receive, again, random notifications till the end of the study, right? What's the contrast in the outcome of that person? That's the excursion effect. And you see here vividly, we're taking an excursion at time t. Okay, so I will simplify the notation a bit. I'll write yat equal to 1 minus yat equal to 0, because all the other a's are so-called natural. All the other a's are naturally assigned according to the MRT policy. Okay, this is not standard notation, but for the presentation, I'll use that to make it more shorthand. Okay, before we move on to the mediation, I wanted to give you a more concrete example of the total of the excursion effect, what it looks like in a specific generative model. You will see some interesting phenomenon going on. So suppose y equals this. Very simple problem. A is always simply randomized. We have each AT influencing Y, but also there's an interaction between adjacent treatments. Here I'm assuming a negative adjacent treatment interaction. So to capture the fact that sending notifications all the time would decrease the effectiveness. Okay, so in this case, with some simple calculation, we can show that the excursion effect equals for AT equals beta t and some other terms. These other terms naturally they come from this negative interaction. Okay, so now one interesting observation is that suppose you consider two micro-randomized trials with different randomization probabilities. Here, the treatment effect of AT on Y depends on the randomization probability. So different trials, you will have different truths. That's very different from RCT, where the randomization is just for the experimental purpose. It's just for maybe efficiency considerations and for getting rid of confounders. But in here, the randomization serves yet another purpose, that it helps to define, it contributes to the definition of the causal effect itself. Now, some might argue, that's not good. If we run two different trials with two randomization probability, how can the treatment effect differ, right? There is no universal treatment effect. Yes, there is no universal causal excursion effects anymore. And if you think about it, it's expected in this setting. If different treatments at different times interact with each other, whether you send adjacent treatment more often or less often should affect the current treatment effect, the effect of the current treatment AT. So that, I would say that's a feature, not a bug. But to be honest, when submitting papers on this topic, I often had to convince reviewer why we're doing this. Okay, so now we'll delve into mediation. First, I'll give a quick overview of the classical causal mediation framework, then we'll generalize that to longitudinal setting. Okay, so now we have this trio: A, treatment, M, mediator, and Y, outcome. A can affect Y directly or indirectly through M. So the potential outcomes are defined like this. M is mediator, it can depend on A. Y, it can depend on both A and M, so that's the potential outcome of Y. There is yet another potential outcome, or I should say a special case of this that's of particular interest, is Y given A and then M at A prime. So this means the outcome we're imagine a world where we assign the person little a for treatment, but we set that person's mediator value to what it would be under a different treatment, A prime. So imagine A is 1, A prime is 0, for example. And this is so-called the cross-world outcome. And that's a way for us to tease apart, at least conceptually, this pathway and that pathway. We're imagining activating this pathway and deactivating the other one, or deactivating this and activating the other one by setting different A and A primes. So, okay, so more concretely, the total effect of A, this is the total effect of A on Y. It can be decomposed into the indirect effect, so expected this difference, where we're saying assign A equal to 1 for both the Y and the M, versus setting A equal to 1 for the Y, but A equal to 0 for the M. Okay, so this way you can see this captures the effect of A through M, but not directly through Y. In the context of HeartSteps and physical activity context, this could be how much long-term improvement arises through increased short-term activity. So in this case, the short-term activity is what we measure in the short term. Then the direct effect is defined in a similar way, so that indirect and direct add together equals the total effect. So the direct effect is A equal to 1, but A equal to 0 for M versus A equal to 0, period. Right. So here, this contrast, you have the A on Y being different. Y1, A equal to 1 versus A equal to 0, where A on M is the same. So that tells you this orange path. Okay. So in our setting, this could be benefits of the prompts on the long-term clinical outcome through other pathways. Could be motivation, habit formation, delayed effects, what have you. Okay, even though, I mean, we'll talk more about that. Right? Here it's pretty clear, it's direct effect, but in our setting, there could be other things in the path. All right, so how do we generalize that to the longitudinal setting when we have many treatments, many mediators? The challenge one we already presented, right? In terms of many treatment medications, we use the marginal contrast idea, the excursion effect idea. Challenge number two, we have many mediators, even if we focus on the excursion effects. There are many downstream variables to decompose. What do we do? Our solution is to, again, simplify the problem, focusing on a simple decomposition. For any t, we only distinguish the following two paths: at to mt to whatever, there could be other variables in here, to y, versus at not through mt and to y. Okay, so I will further illustrate this. We have talked about these random and fixed treatment assignment mixed together as excursion policies. In order to talk about mediation, we will again define some cross-world quantities so that we can tease apart the direct and the indirect effects. Okay, so I will define this theta. It will occur repeatedly later on. Theta t super AB as the following. So the expected potential outcome where y is assigned at time t treatment equal to A, and then all these other mediators also assigned this setting treat AT equal to A. But for the mediator at time t, I'm setting AT equal to B. So this is a way to sort of single out the influence of A on MT. Right? I'm setting something different for MT, but everything else, they're getting little a for AT value. I'll use this notation. Y super AT equal to A, but AT equal to B for MT. This is essentially what it is, because everything else are natural assignments. Okay, and then piggybacking on my rainbow color illustration, here I draw it in iPad, so couldn't have rainbow color anymore, but these shaded dots are the micro-randomized trial policies. These are supposed to be the rainbow color treatment assignments. And then at time t, we're splitting the treatment A in that hypothetical cross-world scenario where we're setting AT equal to A for all the downstream variables, all the future m's and the y, but then we're setting AT equal to B for the current m. And then we come back to the rainbow color, the MRT policy. Okay. So we will be looking at assigning treatments in this way and considering different types of contrasts of a and little b would lead to the mediation effects. All right. So first of all, the total effects that we already talked about earlier. We'll decompose it into an indirect effect and a direct effect. The indirect effect is setting AT equal to 1 and AT equal to 1 for MT versus AT equal to 1, but AT equal to 0 for MT. So this is a way to isolate out the path of AT through MT and through possibly future variables to Y. In the example of HeartSteps, this is the effect of AT on Y through increased immediate walking. The direct effect defined in the parallel way, AT equal to 1, but AT equal to 0 for MT, and AT equal to 0, and AT equal to 0 for MT. So this is talking about the effect of AT on Y not through MT. It could be through other future variables. Here, for simplicity, I'm calling it direct effect, but it's not really direct. It's just not through MT. So here is an illustration for just 2 time points. To the left, suppose I'm decomposing the effect of A1 on Y. So we have XA, XA, Y, and then the ends fully connected. The indirect effect is A1 through M1, then through everything else into Y. The indirect effect is all these paths added together. Then the direct effect is from A1, not through M1, but through could be possibly anything else, and then go into Y. So the direct effect is all these orange paths added together. So now I will need to justify why I do this particular decomposition than any other decomposition you might think of, or decompose it in a more complicated way. So there are a few reasons. The scientific reason is from the very beginning of the talk, we said all these intervention development, they're based on this premise. Prompt, immediate target, long-term goal. So here we're capturing that exactly. The statistical reason is that we are reducing the number of parameters. We don't want to decompose it into too many complicated paths. And there is a more subtle causal reason. It's that it improves the plausibility of certain identification assumptions. So for those of you who are familiar with mediation analysis, there is a critical assumption called intermediate confounding. And that's very hard to satisfy oftentimes. You need to really make an assumption. This is even more complicated issue than, say, our usual unmeasured confounding assumption. I'll delve a little bit deeper into that on the next slide, but you will see that by only focusing on current mediator, the MT, we can get around that issue a little bit better. Okay, so the next step of after we spend a lot of time defining causal effects, I think that's the crust of this presentation, is to convey to you that even with such a hard problem, we can still define meaningful quantities, and then I'll show you how to estimate them. But the definition is really the innovation here. But then the next step is to do the identification. We make some pretty standard causal assumptions: Sutva, positivity, sequential ignorability of A, which is fine. We guarantee that because we are in the experimental setting, and positivity of M. Then there is this fifth assumption called cross-world ignorability of MT. This is an assumption similar to no unmeasured confounding that's not verifiable from data, but this is even more than that. Okay, so let's read this assumption a little bit. So this says this independence, conditional on some history. The conditional is not that important. What's important is you look at the value of MT. This is saying the outcome under a arbitrary MT is independent of the actual MT under a different treatment assignment. Why this is called cross-world? Because this is talking about MT under one treatment value, and then Y and everything else under a different treatment value. In practice, we never observe the two at the same time. So we can never check if the joint distribution of these potential outcomes under different treatment trajectories are independent or not. So this is assumption unverifiable from data. Now, there are still ways to make it more plausible. First is that suppose we measure enough variables in the history so that we can adjust for this MT-Y confounding. Because after all, this is about potential outcome of Y independent of M. So that resembles the unmeasured confounding or conditional ignorability assumption. But there's one more issue, is that we can't have variables measured after AT that influence both MT and YT. If there are such variables, that would be called an intermediate confounding or post-treatment confounding. If there exist such variables, regardless of whether we observe them or not, this assumption would always fail. So that's why I alluded to earlier that this is even more nuanced and complicated than the unmeasured confounding. So now, if MT is measured immediately after AT, that helps with this assumption, because it's harder to imagine, some variable measured between AT and MT if the time lag is very short. But then if we want to think about AT mediated through a future variable, MT plus 1, then this becomes a real issue. Okay, So this method actually only applies for this particular decomposition. All right. Now from here on, everything is pretty straightforward, lift directly from the literature. So we have identification of the cross-world quantity. If you have ever done any mediation analysis, even for single time point, you will see similar expressions. A potential outcome can be identified through either a G formula type of expression or a IPW type expression. Okay. I won't delve too much detail into this, but if you're interested, we can chat more afterwards. Okay, and then I'll show you an estimator. Okay, so remember that we were talking about, in the definition, we always focus on the single time point. We say, oh, AT, what's that effect on Y, right? So that decomposes into the direct at T and indirect at T. At the end of the day, there are many time points, so we'll have to build a model to smooth it out, to pull across different time points. So we'll say the direct effect at T is some model, parametric model over T, and similar for the indirect effects. Maybe you build a quadratic time trend. You can build a spline time trend. Okay, and then the estimation proceeds as follows. Suppose first we estimate all these theta quantities, the expected cross-world outcomes. And the most straightforward way would be to use these expectations. You just put hats on everything, and then you can estimate them, right? That's the first step. Second step is to, once we had the hats of these, we just do irregular regression to get the alpha and the beta hats, so that we can plot the trajectory of the time varying indirect effect and the time varying direct effect. Okay, now in order to estimate these thetas, there are robust estimators for that. This is our very familiar AIPW estimator, right? We have and after all, some of these thetas, they are not cross-world. They are the same A for M and Y. So we can use the AIPW and they are robust. They're doubly robust in general, but in our case, where we know the propensity score, it's a trial. So it's robust to arbitrary outcome misspecification. And then to estimate the genuine cross-world quantity, there is also literature that proposed a multiply robust estimator for this. This was actually a contribution from Johns Hopkins by Elias Spitzer and Erich Chucken in way back in 2012. Now we lifted their approach from a single time point to longitudinal setting, but because we decompose the problem in such a way that we don't need really to model the correlation over time. So the estimator becomes very simple. So I won't go into too much detail of this, but you see that we have some weighting going on here, and we have a residual, and then we have another type of weighting and another type of residual, building a regression model based on different sets of history variables. And then at the end, we have yet another augmentation term. So what's nice about this is that in the micro-randomized trial, when we know the randomization probability, we know the P, then it's doubly robust. It's not fully robust, meaning we still need one more nuisance to be correct. That's either the Q, which is similar to propensity score, but further condition on M. So it requires you to know something about how A influence M or model that correctly. But after all, this is logistic regression. So this is, binary outcome. So usually it's easier to get that right. And then, or the mu T, which is an outcome regression to be correct. Okay, so this is doubly robust. Then after all, if we put everything together, the estimator will be doubly robust. We only need to get one of the two, Q, the propensity score, or mu, the outcome regression correct. And then just wanted to show you one more interesting thing. The first time I see this, I was blown away. I didn't know there was a world existing beyond double robustness. So this is, if we were to deal with an observational setting, then this is quadruply robust. Or in the literature, depending on the parameterization, sometimes people call that triply robust, sometimes people call that quadruply robust. But the way I'm parameterizing it we need either of the four requirements, the four sets of nuisance models to be correctly specified to have consistent estimator. Okay, so this is quite interesting. If you go through the derivation, you see magically things canceling out here and there. And then the theoretical foundation behind all this is still semi-parametric efficiency theory. So the same theoretical foundation that led to the AIPW estimator was also applied in the mediation setting. That's how the authors developed these type of estimators for the single time point case. Yes.
Well, actually, I'll let you continue. I'll come back.
Okay. So lastly, I'll briefly show you our application. Go back to the study. What do we find? As a reminder, we have 37 participants. Here I look at the first 5 weeks as the AT period, and then I look at the last week to define the outcome. Now there's a little bit of an issue in the interpretation because at the last weeks they're still receiving treatments, right? But once we acknowledge that and be careful about the interpretation, that's still valid. The reason I'm doing this is because I don't really have their cardiovascular outcomes. The physical activity is all I have for this data set. We have the ATs 5 times a day. We have the MT 5 times a day. Okay, and so these are the direct and indirect effects put in this context. I'll keep reminding you what they are when we see the plots. And in terms of the particular model fitting, I used B-spline basis over T to give you a smooth curve. And I used generalized additive models for the nuisance parameters. So here is the estimated effects along with their confidence intervals. You see 3 lines. The green represents the total effect over time. So for example, early on, this is how does sending a notification early on influence the outcome at the end. This is how does sending a notification later in the study influence the outcome at the end. Okay, outcome is always at the end. When we talk about early or late, that's just the treatment time point we're focusing on differs. So that's the total effect. You see a big bump at the beginning, then it's 0. Meaning later on in the study, people don't really pay attention to these notifications. Early on, it still matters. Then we see 2 other lines. The orange, I kept using orange for the direct and the blue for the indirect. So in this case, it's a little bit of a brain puzzle, but indirect effect is through the most immediate outcome. Direct effect is everything else. Okay, so indirect effect is really what the behavioral science theory was going for, the premise, the chain that we were talking about. Okay, what do we see? Let's see. First, we see that early direct effect is large, but declines rapidly. It explains most of the total effect. In fact, it tracks the green line pretty well. And then for the indirect effect, it's pretty small in magnitude. If we were to zoom in, you will see that there is some, point-wise significance around here. I wouldn't pay too much attention to the p-values because if you want to go full rigorous, we should have developed confidence bands. And here, this is just illustration, so I'll have to ask you to live with that. But then the indirect effects, they don't decline as drastically. That's another observation. Now, if you were to say the indirect is not there whatsoever, I wouldn't argue with you. But if you please follow my narrative that the indirect effect is more stable. They still decline, but not that drastically. Okay, so the scientific takeaway from that. Now I'm doing some kind of stretch here by trying to put a clean interpretation on things, but we would say here again, orange is the curvy thing that is the direct effect, right? Early on, the prompt's effect on Y are through pathways other than immediate walking. So if I send you a notification in week 1, how does that change your outcome at week 6? It's not that it added to your step counts on that day, but rather it maybe planted a seed in your mind so that you know, oh, I should walk more. Now, later on in the study, the later prompts they are more indirect effects. So it's more through increased immediate walking. Now that I admit, that's a little bit of a stretch. But then there are still lots of open questions. For example, what constitutes the pathways other than immediate walking? Just now I said maybe it planted a seed in your mind. That's just my conjecture, my heuristic. But how can we validate? What measures do we need and what methods do we need to validate what's happening? What is the mechanism of motivation, habit formation, and all that? Right. And also why pathways, this other than immediate walking pathway, no longer effective later in the study? Is that people don't look at the phone anymore? Is that because habituation? Or maybe it's because that our intervention has worked. People have already developed the habit. So later on, whether you send notification or not, doesn't matter anymore. The first few weeks are good enough for them to develop a exercise habit. That could be an alternative explanation. And we will need more data and better methods to answer these. Okay, and lastly, there's this technical concern of sensitivity to the cross-world ignorability assumption that right now we're working on sensitivity analysis methods to handle that. All right, so to summarize, the motivation of this talk is we wanted to quantify whether the short-term responses mediate long-term effects of the mobile health interventions. We looked at two challenges, both related to having so many time points in the study. And then we defined interpretable and estimable effects to tackle these challenges. And then we discussed some finding from the HeartSteps Micro-Randomized trial. And before I open up for questions, I wanted to share with you some photos that was from 10 or more than 10 years ago that I took when I was in the department. And you see some familiar faces there, and also some of the faces in the audience, possibly. Okay. I was digging through my phone. This was the first picture I have. I joined the department in 2012. I guess my phone back then was lost and I don't have the pictures anymore, but there was Vadim lecturing me on the algorithm. So I still don't know what it is. But this was methods, the second year methods course. And then this was causal inference working group, open house. You see Betsy leading the group and showing some comics there. And then we see more of these. We see Liz Stewart talking about her work. And then Michael sharing his passion for kale. Okay. I don't know if any of you have seen it, but back in the days, Michael has a very big poster of, kale is something, the world, or I love kale, something like that.
Yeah.
On his store. That's the first time I learned kale, and I tried to taste it. Okay, and then, yeah, a very dynamic picture. With permission of Michael, I'm sharing that with you all.
It's too bad Dan.
Yes.
Here to appreciate.
Dan is at Utah now.
Jelly in the background.
Yes, Michelle is still around.
He's around.
Yeah.
Oh. I don't know.
What's the question?
If John Michelle was a student.
He was a student. He was with my same cohort. Yeah, he started PhD in 2012, even though he has been working for a while before then. Yeah.
Right. Oh, wow.
Yeah. Okay, and then back in the days, I'm sure you still have a department cultural mixture. There was Karen talking to some student, and then somehow in the department cultural mixture, I don't know why Vadim is talking to student about math. Maybe that's the culture. And then I also remember back in the days, and I see the newsletters Liz sent out all the time, so I know that you still have these chili thing. I don't remember the name. Yeah, the chili party. Yes, that's a lot of fun. And then there was another seminar in the Genome Cafe. I think it's the Slam group by Mei Chen. Yeah, and then some students and faculty grabbing food. I guess back in the days, that was my highlight of the week is every time we have free food in the department, either student seminars or what have you. And then this was uh there was a room always with seasonal decorations, whether it being
Crowell's.
okay. I never knew what was it, but yeah,
That's good.
I see. Yeah, Halloween's and Christmas, everything. That's so great. And then lastly, one thing I miss is the crabs. This was not in the park. This was at Costas Inn. And I think now the bridge is destroyed. You need to take a longer route to drive to that area. Yeah, the other day I was hearing on the news the bridge will be rebuilt in 2030. Hopefully we'll see the bridge again. Oh, Jessica's office. Betsy is commenting on. Yes. Okay, so that's all I have. Thank you very much, and I'm happy to take questions.
It's big.
Yes.
Did you look at like data?
Oh, great question.
Like it actually worked with the change.
Right. Yeah, that's a great question. So treatment heterogeneity, we didn't. Or I should say two parts of the answer. There's usually two parts to an answer. Yes and no. Yes is that for the total effect, we have looked at the treatment heterogeneity, where we can condition on either baseline covariates or time varying covariates, look at the effect of AT on Y. That we did. For mediation effects, we haven't done that. We actually are working on the paper to incorporate that. You may notice that everything I presented today is fully marginal, just expectation, not conditioning on anything. So yeah, with conditioning, there's some more technical challenges in terms of what kind of estimator do you use. And then we have found a literature also by Elia on this similar topic. So we are trying to adopt that into this framework. Great question. Okay. Okay. The question is, have I thought about looking at even longer term health behaviors? Yeah, for these micro-randomized trials, that's a great question. For this particular study, this was one of the first micro-randomized trials, and we weren't that sophisticated in the trial design, and we didn't capture even longer term. Nowadays, the newer micro-randomized trials, they often have longer term time measures, like up to maybe 6 months or a year of follow-up, even though the micro-randomization period, you can't have that long usually. It could be like a few weeks, but then after 6 months, we ask the person, have you relapsed, for example? So yes, we will be able to do that. Okay. And also, if anyone on Zoom has any questions, feel free to unmute yourself. Did you have a question earlier?
I have a question, but I want to give everyone else a chance. Okay. Any questions from Zoom or from anyone else? Well, I was well. First, thank you for the excellent talk. It was a crystal clear talk on a very complicated topic. And that yeah, I was curious about the in some of the robustness results that you don't need to correctly model the cross world regression. It's as long as you get other things correct, but you still need that assumption about that there's an ignorable is that correct?
That's true. That's true. Yeah, that's a great observation. I never thought about it this way, but you're right. So what Michael was alluding to is that in the assumption, we always have this assumption of the cross-world ignorability and particular type of independence between the Y and the M in different worlds. But then in the estimation, there is a I have the particular form of the nuisance parameter actually at the end. Okay, so here, mu is an outcome regression. And then nu is something called a cross-world regression, where we are regressing the mu for a particular a. Yeah, should have written a equal to little a, but mu for a particular a, regress that on a different a. So this is a cross-world regression, and Michael was commenting on that. In the estimation, for the estimator to be consistent, we don't necessarily need this equation to be correct, as stated in the assumption, the results here. Sometimes it depends on this nu, but sometimes it doesn't depend on the nu. So that's, yeah, I mean, technically it's because the identification here, it depends on the cross-world regression, but in here, there is no cross-world regression. So if we were to use this, but then I guess what's the more fundamental reason behind that? Why we need an assumption on the independence, but not an assumption on the functional form? I haven't thought about it, so I don't know.
Yeah, it's so that it makes sense to me now, at least that it's. I mean, the reason I like that part about not having to be right about your model of the cross-world phenomenon is that you can't get any data.
Yeah.
You have to. It's all you have to. It's to help you with that. So, but you still there's still baked into this independence that you also can't verify. But the independence combined with this allows it makes the inverse weighting part work.
Yeah.
I think,
Yep.
roughly.
Yep. Pretty much. Yes.
But okay, that's super interesting.
Okay. Thank you. Thank you. Yes.
I have a question. You mentioned at the start that you might use this to like come up with something like an optimal strategy.
Right.
And use a second stage randomized trial. Would you like? Is the idea to do that by looking at where the total effect is?
That's a great question. That's a very difficult question, in fact. So here we're talking about the original promise is we can after the micro-randomized trial we can optimize the intervention and then go on to RCT. But how do we do that exactly? Even with all these results I presented to you, what's the optimal policy? There are two approaches that people have taken, not directly from the results of today's presentation. Today's presentation is the more indirect evidence for how you might do that. But more directly, one could use offline reinforcement learning methods, like something like Q-learning. Maybe some of you have heard of, which is directly a way to it's well-established literature in reinforcement learning, and it can use this kind of data structure to learn the optimal policy. That's one approach. The second approach is instead of doing offline reinforcement learning, meaning after we collect all this data, estimate a optimal policy, another thing we could do is do online reinforcement learning, meaning that with the micro-randomized trial data, we could sort of come up with a reasonable starting policy to implement in the RL, but then in the RCT, but then in the RCT, the policy or the algorithm would adapt within each person. So there are additional, I guess, novelties there where we can have the app start with the same reasonable policy across everyone, but then because different people are responding differently, the app would adapt to each different individual. And that I think is where the field of mobile health intervention is moving towards. Yeah, but great question.
Well, I just want to thank Tianchen for coming. It's fantastic to see you, and yeah, you're doing a very impressive work. Thanks for your presentation.
Yeah, thank you, everyone.